Hello friends, welcome to my channel Technobuzz. I came back with a new video under Conjugate Heat Transfer series titled Conjugate Heat Transfer Analysis of Industrial Ovens. I will cover this topic in two videos. In the first video, I will cover introduction and mesh generation. Please do like, share and subscribe. Let's start the video. So in the first video, I will present a short introduction to industrial ovens, creation of geometry for this proof of concept study, then updating the basic conjugate heat transfer folder structure of OpenFoam12. Then I will go to mesh refinement procedures and I will discuss in detail these procedures. So finally, in this video, I will create the mesh for the simulation domain. In the next part, that is in part 2, I will discuss and present the operating conditions and file modifications needed for updating the operating conditions in the OpenFoam folder structure. Then I will discuss the procedures to launch the simulation. I will also discuss the post-processing in ParaView and will present animations for contours, temperature contour, velocity and streamlines. So this is the plan of the study. Before starting the video, I would like to request you all to like, share and subscribe. So let's start the first part of the video. Ovens are heated chambers used in industries for various heat treatment applications, such as heat treatment of mechanical components. This process is crucial in manufacturing industry. It modifies the metal structure to enhance their mechanical properties, making them suitable for various industrial applications. There are different processes such as annealing, quenching, tempering, and hardening. Cure metal coatings. Curing is a chemical process at higher control temperature. This enhances properties such as adhesion, chemical resistance, and qualitative surface finishing. Further, ovens are extensively used in food industry to enhance the quality of food products. Baking, drying, dehydration are some of the processes used in food industry. Oven baking process is a vital step in automotive industry. These are used for preheating, baking, drying of the body in white at different stages of paint shop applications. Food processing. The role of oven in food processing industry is indispensable. Ovens are used for baking, drying and dehydrating, pasteurization, roasting, etc. Added to this, ovens are common in domestic applications. In electronics industry, the wire wound resistors are provided with ceramic coating to protect windings. These coatings, along with other metallic components, need heat treatment to enhance their strength and durability. Some electronic components such as printed circuit boards, integrated circuits, RAM and ROM modules are subjected to burn-in testing, that is, subjected to high temperatures over an extended period of time to test their reliability and durability. In medical industry, ovens are used in lab applications for drying and sterilization of equipment. Additionally, ovens are widely used in pharmaceutical industries for processes such as depyrogenation, apart from other general processes. In aerospace industry as well, ovens are used to enhance the properties of components. As the aerospace components are subjected to extreme atmospheric conditions, efficient heat treatment is very important. Hence, it may be observed that ovens are indispensable in almost every industry. However, based on quality requirements of end products, based on Area of application, quality standards are specified by the regulating authorities. Thus, industrial ovens are to be designed based on industry requirements but within the specified guidelines of regulating authorities. Important parameters to be considered for oven design are listed below. Weight or dimensions of the product to be processed. This, along with the production method, guides the selection of the type of oven to be used, such as batch type or continuous type. Now, heat treatment process to be used based on application and requirements. Different industries need different heat treatment processes or combination of various heat treatment processes. Throughput requirements. Throughput is estimated based on current and future needs. Heating space requirements estimated based on product dimensions, production rate, and future adaptability needs. Baking or heating profile requirements based on end product quality, requirement standards, process time, and production demand. Different heating profiles are specified. Ovens must be designed using a combination of convection, conduction, and radiation processes to match the given heating profile. Heat flux requirements. Heat flux is estimated based on the heating required for specific heat treatment process. Energy requirements. The source of heat generation, such as electricity, fuel-fired, coal, or any other mode of heat generation, is decided based on the required heat flux. Energy conservation plays a predominant role in today's energy demand and cost. Design or selection of auxiliary equipment needed. Industrial ovens are supported by auxiliaries such as conveyors, gears, blowers, belts, chains, and other logistic equipment to support the process. Durable material for oven exterior and interior. Material selection for oven interior and exterior plays a vital role on durability and efficiency of ovens. Materials with high corrosion resistance, capacity to sustain high temperatures for long operating times are selected. Oven design requirements. The efficiency of any heat treatment process in ovens depend on the efficient air flow distribution without any recirculation zones, even or uniform temperature distribution throughout the heating space without any thermal stratification zones, efficient air exit design to maintain proper air circulation and recirculation for energy conservation, consistent maintenance of pressure, temperature, and airflow. The design variables which influence the above criteria are the number of inlets, number of exits, their size and location, inlet nozzle orientation and the airflow velocity, time of heat treatment process, speed of movement of products or components to be heat treated, oven cross section and length. Parametric studies, either experimentally or numerically, guide the designers to design the oven with the best combination of above said variables to achieve the design requirements. Computational fluid dynamics is an efficient and cost-effective tool used by all manufacturers. However, a final experimental prototype testing of the design is inevitable for realistic assessment of the final design. It may be noted that CFD is used in design phase of ovens as well as in the studies for improving the efficiency or capacity of the existing ovens. Having said a lot on industrial applications of ovens, I stop the discussion here. Now let us proceed to geometry creation for the present case. The geometry considered for this study is shown here. The oven is modeled as a rectangular box. Two circular surfaces are created on either sides. These surfaces are treated as inlets from where the hot air at 453 Kelvin is blown at 0.5 meters per second. A velocity inlet boundary is specified. Only two inlets are used in this study for simplicity. Two openings are provided on either sides of the oven. The solid objects to be baked, such as body in white in automotive industry, or a bunch of parts to be baked, move through these openings 1 and 2. In general, symmetric boundary condition is to be specified. This is because the industrial ovens are very long in length, of the order of 15 meters and more. It is cumbersome to model whole oven. Hence, an optimum oven length is considered for simulation and symmetric boundary condition is specified. However, in the current simulation, I specified pressure outflow boundary condition. A rectangular outlet is provided at bottom and a pressure outlet boundary condition is specified. For the present study, I created a simple manifold geometry as shown. I could have used a car geometry, but it needs to be repaired to make it a perfect manifold geometry. Hence, I created a simple object. Now let's proceed to case setup and launch the simulation. Now let's start updating the basic folder structure with the details of current simulation. So let's start first with the constant folder. I have already done, so I will quickly revisit each folder and show the details of the modifications. Okay. Now the first step is geometry. So the created geometry for the simulation, fluid and solid domains are copied here. So in this fluid file, the boundary phase groups are updated. So here we have inlet 1, then we have inlet 2. So this is inlet 2. Then we have two openings on either sides of the geometry. So opening 1, open 1 and open 2. Open 1 and open 2. Then we have wall. So apart from these boundaries, there is an outlet created at the bottom as shown. So that outlet is updated here. So the STL contains all the phase groups needed for this simulation. So the solid object is the manifold object. No need to check this one. So this folder is updated. Then we go to fluid. In this simulation, we consider turbulence. So turbulence properties are updated here, physical properties. We'll come back to this folder while working on operating conditions. Same is the case with solid. So now let us go to group 0. Here the boundary conditions are updated. So we will update this folder again once after creating the mesh. So let us first see the file. So I have already updated this. So here you can see the inlet outlet. All the boundaries are written here. We need to do this. A detailed procedure I have updated in my earlier video. You can visit that video and check the procedure. The link of the video will be given in the description. So here all the boundaries are updated. We will revisit these files before launching the simulation. Okay, all these files are updated. We'll come back to this folder again. Now the main thing is this folder. No need to touch these two currently. So already this folder is updated with turbulence parameters. So we'll come back to that later. So first check block mesh dict. So in this file, the vertices are updated as per the domain limitations. The coordinates of 8 edges are updated here. Here I am using simple grading first with the cells, 65 cells in X direction, 30 cells in a Y direction, and 30 cells in Z direction. So based on the mesh quality, we will revisit this and then we will update again. Then we go to this file is more important. We have to work on this. So here the geometry part, the details of the fluid STL are updated here, fluid, and then the regions, all the boundary phase groups written in the STL file are updated here. And this is the solid STL. So in this section, again we need to update all the boundaries with their patch details, patch information. So here for wall we need to give type wall as a patch information. Okay, now for the solid region, the inside point is updated here. But we select a point inside the solid, and for the fluid region, the point is updated here. So a detailed procedure is given in my earlier video. You can check that. This file is updated. So now we will use the meshing commands and mesh the domain. Okay, so first we will run the commands for meshing. So block mesh. So this is done. Now we go to snappyHexMesh. I'm using only single processor. So now this is done. Then we use the next command. Okay, so here both the regions are created. Now let us check if the boundary groups are identified or not. So we go back to constant folder, open the folder fluid, polymesh, and open this file. Now this is very important. So inlet is identified, inlet 1, inlet 2, open 1, then open 2, wall boundary is identified, outlet, and fluid to solid. This is the interface boundary between fluid and solid. So all the boundary phase groups are identified. So this is fine. Now let us open the mesh in ParaView and check. For that, first let us run this command. So this command creates these files for fluid and solid. We can open this files in ParaView and check the mesh. Okay, let us open these two files. Now select this fluid and let us create a clip in Z direction. Now change the surface to surface with edges. So now here we can see this is a fluid mesh. The solid mesh is here. So we can, so this is the solid mesh. Let me change the color of this solid. Okay, so this is it. You can see here the mesh is not so refined in the interface, and as we are using turbulence model, we need much refined mesh near the interface so that the heat transfer takes place efficiently. So let us refine the mesh. Now we have two files to play with. One is this file, the other one is this. Now let us start with this file. Let us refine the mesh using this file. So as a first step, let us go to this refinement surfaces. We do have 0, 0 and here level 1, 1. So let us make it 1, 2 and here also 1, 2. Let us see how this modification is going to improve the refinement. Okay, so let us see the mesh. To avoid the repeated terminal activities, I skip that part and I'm showing the main mesh modifications only. Okay, then let's go to fluid mesh and then create a clip in Z direction and play. This is what we see here. The middle one is the mesh. Okay, so let me change the color of the solid. So this is it. So here you can see not much refinement could be seen. It is nearly similar to the one which we have seen earlier. I don't know why these lines are coming, but this I have noticed as a center Z only. If we change the section to the other point, so show plane, let us move further. Okay, then create the section. Yeah, so if you see here, the behavior is slightly different. I don't know at the center what has happened, but here at this section, that is at Z is equal to 0.2385, we can see this kind of refinement. So let us fix to this point and see how it further refines with our further modifications. Now let us open this file and refine further. Here we see add layers as false. Let us change this option to true and test. Okay, now let us test the mesh. Now with this new modification, that is we change this add layers option to true. We see that there is not much variation seen here, but I think some layers are added. Okay, so there is no much change here, but still it is fine. We'll continue with that layer as true, and then we will further modify the mesh. Okay, so as a next level of refinement, let us check the other options here. We have made it level 1 to 2, 1 to 2, and then okay. Now let us, here we see n cells between the levels. So let us change this value from 1 to 5 and check how the refinement is affected. The mesh is something like this. Now we can see some considerable change in the refinement near the solid. So here this is the solid. So let me off this. So you can see the mesh near the solid has considerably refined when we increase the number of cells. So the refinement seems to be fine. Further, let us check what we can do more. Now let us open this file again, and we go further down. Here we see the variable expansion ratio. Let us increase this value to 1.5 and see how this parameter is going to impact the refinement. Now with this new refinement, when we increase the value of expansion ratio from 1 to 1.5, I see this kind of mesh here. Seems to be fine. For this kind of simulation, I feel this mesh refinement is okay, but further refinement is always possible based on the application, the requirement of the quality of results. We can further modify the parameters and refine the mesh near the interface. As I told, the quality of result depends on the mesh refinement near the interface and other areas because we are using turbulence model. Okay, so further comment here, we can increase the number of cells in the block mesh dig file also to increase the refinement, but I would like to stick with these values only here. The reason is this is a demo case. The other thing is, if I increase these numbers, then the computational time will increase. So I don't want to touch this. I would like to have an optimum mesh so that my result is qualitatively and quantitatively good. So here I present few mesh refinement trails I carried out. Keeping with all variations, the mesh with expansion ratio 1.5 seems fine and optimum. I continue with this mesh for the further simulation activities. The refinement of this mesh in X direction is shown here. This seems to be fine, and I continue with this mesh. It may be noted that more parameters can be varied for much better refinement. However, for this proof of concept case, this refinement should be fine. Further, it may be noted that the type of application also influences the refinement. For research analysis, a finer mesh is considered for qualitative purposes. However, industrial studies include efficiency improvement and design optimization activities where Optimum refinement of mesh should be fine without compromising the quality of the results. So friends, I end this video here. In the second part of the video, I will further discuss the case setup, simulations and post-processing. Stay tuned and please like, share and subscribe.